Good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. In this lecture we are going to discuss about one-dimensional infinitely rigid box, or it also can be called as infinite deep potential well. So actually what is the situation? That is a one-dimensional motion. So this will be the physical situation that a particle is moving only along x-axis in between the range or in between the length 0 to L. So in between the length 0 to L is particle is moving to and fro motion, but it could not be escape from beyond the L and this side beyond the 0. From this side it could not be penetrated, from this side it could not be penetrated. Means here the wall is a rigid wall. The particle could not be penetrated this wall. So particle is bounded to move along one dimensional, along x-axis in between 0 to L, or the length of the particle motion is L. Okay, so this situation or this physical dynamics is represented mathematically here. That means this at x is equal to 0, the potential is infinite. What is potential? I am going to be discuss somewhat. Wait, here at x is equal to 0, this is the wall. The particle, suppose this is the electron, could not be penetrated this side, and at x is equal to L, another wall, another rigid wall will be present, due to which this particle could not be penetrate this wall. Okay, that means the particles has not that much energy. Suppose E is the energy of this electron could not be penetrate or could not be passed through beyond x is equal to L, beyond x is equal to 0. That means we can consider that a heavy negative charge, if it will be present over here, heavy negative charge, then a repulsive force will be created due to this negative charge. So whenever the electron will be come at the x is equal to L, suddenly that electron will be feel a force due to which it will be repulsive. A repulsive force is going to be perceived by this electron exactly at x is equal to L. Similarly, here if a large negative charge will be present over here this side, or we can say at x is equal to 0 only, when the electron will be moved this side at x is equal to 0, it will be perceive a highly repulsive force. That's why the electron could not be penetrated this side, could not be penetrated this side. Or we can say the potential will be infinite. The potential is infinite at x is equal to A, potential is infinite at x is equal to 0, and the electron or the particle is moving freely inside this length, not all over the area I am here. This situation is represented over here, means electron is moving like this. So from x is equal to 0 to x is equal to L, electron freely moving, means there is no experience of external force. That means potential will be equal to 0 in between x is equal to 0 to x is equal to L. However, potential is infinite at x is equal to at x is equal to L, and potential is infinite at x is equal to 0. Okay, so because we know that the so-called potential means you have to remember that that electric field is defined as minus dV by dx, right? Here V is the potential, right? So V is nothing but minus E dx. So here E is nothing but the so-called electrostatic field intensity, electric field intensity, and dx. So electric field intensity means the force per unit positive charge, and dx. So here the potential is defined as one type of unit of work done. So work done can be possible if we have external force. if we have a external force, then a work done or a potential can be developed. So here the potential at x is equal to L, the potential is infinite. At x is equal to L, at potential is infinite. X is equal to 0 at potential is infinite, because we can imagine that exactly at x is equal to L, the force due to repulsive force, due to suppose a higher negative charge will be much more, that the electron could not be passed through or penetrate the position x is equal to L and x is equal to 0. Okay, so these things whatever we discussed I written, I am just reading quickly, you just observe. Let us consider one dimensional motion of a particle along x axis, figure 1. This is figure 1, this is figure 2. Okay, I am going to put a dotted line, it will be separated both figure 1 and figure 2. So figure 1, this is figure 1 and this is figure 2. So figure 1 represents a particle having mass m moving along x axis in a hollow cylindrical bar having length is L. This is the length. In this case the walls are considered as so rigid that particle could not be penetrated. That means here we have to consider a rigid wall, So this is the wall is rigid, means so hard, that means the particle don't have that much energy, it can be passed through that rigid wall. So mathematically the particle dynamics, whatever in our figure number 1, it can be represented by figure number 2. That figure number 2 represents, this figure number 2, what it is represents, a 1D potential well for which potential at the two ends of the well is infinite. I written over here infinite. Okay, but 0 inside the well, what we have been discussed. See, these things you should not be write in your note. This figure, this much you have to write in your, draw in your figure. Okay, and you have to pause the video and you have to write the note, because useful will be for your exam purposes. So but 0 inside the well, so that means potential, what we discussed, the potential will be infinite at x is equal to L and x is equal to 0 and x is equal to L, and potential, that means that there is no force, external force in between a 0 and L. So here the particle in this area, in this length, the particle can be moved without experience a force, means freely. So here one can imagine, so here I am going to so what it is written, figure 2 represents a 1D potential well for which potential at the two ends of the well is infinite, but 0 inside the well. Here one can imagine that particle can move freely, no force in between 0 to L, but beyond this range a strong repulsive force experienced by the particle due to which it cannot be penetrated. So in this range 0 to L, the particle is moving freely, but at x is equal to L and x is equal to 0, the particle experienced, or you can write perceived or gets a strong repulsive force. So we can write, but beyond this range a strong repulsive force experienced or perceived by the particle due to which it cannot be penetrate this range beyond x is equal to L and beyond x is equal to 0. Hence box, the so called box, whatever we have been represented in this figure, it can be written in the mathematical form as Vx will be equal to 0 in the length 0 to L. In the length 0 to L, the potential, that means it indicates one type of the force will be equal to 0, external force will be equal to 0, but beyond x is equal to 0, beyond x is equal to L, and also at x is equal to L and beyond that, at x is equal to 0 and beyond that, the potential is infinite. So in between 0 to L it is 0, but less than that of the x and greater than that of the L, you have to write this one, at x is equal to, less than equal to, greater than equal to, will be equal to how much? It will be infinite. So let this is equation number 1. This is equation number 1. Now we have to consider, now we know that any quantum mechanical behavior should have to be followed by Schrodinger equation. That means if we have to consider a quantum mechanical dynamics, and if it will be follow the Schrodinger equation, then from the Schrodinger equation we can found its the behavior, nature of the exact nature of the behavior. That means blindly that quantum dynamics should have to be follow the Schrodinger equation. So we know that in general one dimensional time independent Schrodinger equation of a particle which is moving in a force field in general 1D time independent Schrodinger equation, particle moving in force field, what is that? That is del square. This is del, okay, del square psi by del x square plus 2m by h cross square E minus Vx psi will be equal to 0. So here potential is considered only function of position, not time. That means potential whatever we have been considered, or the situation whatever we have been considered in this here in this problem, here the potential is fixed, not changed with time. Okay, only changed, the potential value is changed with the position. That means in between this it is 0, at x is equal to 0, beyond that at x is equal to L, beyond that it will be infinite. And but here in our case, so this is the general form of time independent Schrodinger equation, where potential is only depends upon the x, not depends upon the time. But here in our case, okay, here it has been considered that del square psi by del x square plus this much term, this much 2m by h cross square E minus Vx is considered as k square, or this. So this equation number 2 also can be written as del square psi by del x square plus k square psi equal to 0. Let this is equation number 3. So this is our general form of time independent Schrodinger equation of a particle, of a one dimensional motion of the particle. This is the general form, equation number 2, and it is equation number 3 only. Here for equation number 3 we have been considered that 2m by h cross square E minus Vx is k square. Okay, now we are going to find out what will be the wave function of the particle outside the box. See, here physically we have been discussed that this is the rigid wall, this particle could not be penetrate this wall. That means the existence of the particle outside the box is how much? Is 0. That means the wave function of the particle outside the box also will be 0. So that will be extracted or found out by this derivation. You just follow it. So the wave function of the particle outside the box, that we are going to found at end from the discussion, that the wave function outside the box or the existence of particle outside the box will be 0. So for that we consider psi 1 be the wave function exists outside of the well. Okay, as we discussed, particle could not penetrate the boundary at x is equal to 0 and x is equal to L. That is, the energy of the particle is not sufficient to overcome the potential at x is equal to 0 and x is equal to L, or the repulsive force. So these things we have been already discussed. That means if we are saying that particle could not be penetrate this wall, or particle could not be moved beyond x is equal to L and x is equal to 0, that means when the particle is reaches at x is equal to L, a strong repulsive force experienced by the particle. and here also when it will reach at x is equal to 0, also it will be experienced a strong repulsive force. That means we can say the energy of this particle is not that much enough that much that it can be overcome the so called repulsive force. Whatever the repulsive force is experienced over this particle, that repulsive force is higher, much more higher than the energy possessed by the particle. So only for that the particle could not be penetrate beyond x is equal to L, beyond x is equal to 0. Okay, that means the energy of the particle is less than that of the potential. Okay, at and beyond x is equal to 0 and x is equal to L, at x is equal to 0 and beyond x is equal to 0, at x is equal to L and beyond x is equal to 0, or we can say outside. Okay, now the equation number 3, this equation number 3 will be in the form of what? See here, k square is written as 2m minus vx by h cross square. Okay, k square is written as 2m minus v by h cross square. Here k square is positive, and here it is considered as E is greater than that of the Vx. E is greater than that of the Vx. So k square is positive, that means E is greater than that of the Vx. So 2m minus Vx by h cross square is considered as k square. But for this case beyond the x is equal to 0 and x is equal to L, potential is greater than that of the E. Okay, potential is greater than that of the E. So hence k square will be the negative. So E minus V will be negative, so it will be negative. That means del square psi 1 by del x square. Here we consider that let psi 1 is the wave function exist in the outside of the well. So here the equation number 3 can be modified to del square psi 1 by del x square minus k square psi 1 equal to 0, because here the k square will be the negative, because here bx is greater than that of the E, so it will be minus k square, will be considered as minus k square will be this much. Here minus k square will be nothing but 2m by h cross square E minus Vx. So imply that k square will be 2m by h cross square Vx minus E equal to let it is equation number 4, and this is equation number 4 and this is equation number 5. Now the solution of equation number 4, see this is the equation number 4, and if we are going to find out its solution, this is in the form of m square k square minus k square is equal to 0. So the two roots are m equal to plus or minus k. The two roots are plus or minus k. Hence the solution of this equation number 4 will be how much? It will be psi 1 equal to a e to the power kx plus b into e to the power minus kx. Let this is equation number 6. The first term, this term of this equation number 6 could not be acceptable. Why it could not be acceptable? See, as x tends to infinite, if we are going to consider this first term, that means if we are going to consider at x tends to infinite, at the infinite, this term will be infinite. But boundary condition tells that at x infinite, x tends to infinite, psi should be tends to 0. But psi should be tends to 0. This is our boundary condition. But from the first term, we can found that if x tends to infinite, psi 1 tends to infinite. So only for that this first term could not be acceptable, because boundary condition tells that if x tends to infinite, psi tends to 0. That means at the end of the infinite, the existence of the particle will be 0. There is no existence of the particle. Okay, this is according to the boundary condition that we know. So hence acceptable wave function will be how much? The acceptable wave function, if this will be not acceptable, the acceptable wave function will be psi 1 equal to b e to the power minus kx. Let this equation number is 7. Now from figure 2, it can be found that when x tends to 0 and x tends to L, Vx tends to infinite. Okay, so from equation number 5 it can be found again from equation number just word AGAN, again from equation number 5 it can be found that Vx tends to infinite when k tends to infinite, because see, from equation number 5 Vx, if Vx will be infinite, tends to infinite, obviously k will be tends to infinite. Okay, so here you can see that when x tends to infinite or x tends to L, Vx tends to infinite. But and also from equation number 5 it can be perceived that if Vx tends to infinite, k also tends to infinite from equation number 5. So it is written that from equation number 5 it can be found that Vx tends to infinite, that means for Vx tends to infinite, k tends to infinite. So hence from equation number 7 we can conclude that if k tends to infinite, the e to the power minus infinite, that means 0. We know that e to the power minus infinite will be 0. Okay, so from the equation number 7 it holds that I am going to draw that figure here, x is equal to 0 and x is equal to L. Okay, so here it is telling that if we have to approach towards x is equal to 0 or x is equal to L, the Vx will be approaches towards the infinite, and here also Vx tends to infinite. Okay, if Vx tends to infinite at x is equal to 0 and x is equal to L, see from equation number 5, if Vx will be tends to infinite, k tends to infinite. Hence, if x tends to 0 or x tends to L, this k will be tends to infinite. That implies psi 1 will be equal to 0. And beyond that also the same. Beyond that potential will be infinite. Beyond that potential will be also infinite. So whatever we have been defined here as the potential, that x less than equal to x greater than equal to L, it is infinite. So beyond this infinite. So hence at x is equal to 0, beyond the x is equal to 0, at x is equal to L, beyond the x is equal to L, the psi 1 will be found as 0. That is here it has been written that. Hence from equation number 7 it can be concluded that as k tends to infinite, psi 1 tends to 0. Okay, that means at x is equal to 0 and x is equal to L, and beyond this range wave function of the particle does not exist. Okay, so here in this way we have been found that wave function of the particle outside the box is 0. That means outside the box the existence of the particle is 0. There is no existence of the particle outside the box. Okay, so next we have to discuss wave function of the particle inside the box. So what will be the wave function of the particle inside the box? So here we consider that let psi be the wave function inside the well, that is in between 0 to L. Let psi be the wave function. What will be the psi value that we are going to be derive? That means inside the well means in between 0 to L, x is equal to in between 0 to L, the Vx is how much? 0. Hence the Schrodinger equation has the form, that means using equation number 2. Now if you are going to use the equation number 2, then and we are considering the Vx will be 0 in between 0 to x is equal to 0 to L, then this equation will be written as del square psi x by del x square plus 2m e by h cross square psi x equal to 0, or many books it is written in this way that this is double derivative of psi x, so it is written it can be written as, or many books they have been written psi double star x plus 2m e by h cross square psi x equal to 0. But here in our discussion we are considering in this form. Okay, and let k square is 2m e by h cross square. 2m e by h cross square is considered as k square. So this equation will be del square psi x by del x square plus k square psi x. This is function of x. Okay, psi function of x. Here also it is written psi function of x will be equal to 0, and let it is equation number 3. See, you can ask that here it is ended with equation number 7, and you have been started that equation number 3. Here it is equation number 3. No, actually what I am going to say that if this question is going to be asked in your exam, so I will be suggest that this part you should not be right. This is this part, the wave function of the particle outside the box, here I have been derived, or here we have been discussed for understanding purposes. Okay, if the question is asked in your exam on the one dimensional infinite rigid box or infinite deep potential well in your exam, it will be up to 8 to 10 marks. So for that, this portion no need to write. This portion is only for your understanding, only for that I discussed. So where you have to be start from here for exam, from here you have to write for this question, from here you have to start, but you have to write with considering the precising the writings. Okay, so you have to precise this overall writings, and up to equation number 2 you have been written. Okay, then you have to start from here. Okay, from here that the Schrodinger equation has in the form in the range of 0 to L in the form from equation using equation number 2 blah blah. So let's we have to discuss. So this is the equation number 3. Okay, so for exam point of view, you have to write up to equation number 2, then you have to start from here. So only for that, this is the equation number 3 I considered. Okay, the general solution of equation number 3 will be psi x. This is psi function of x equal to c e to the power ikx plus d e to the power minus ikx, because the equation number 3 is in the form of m square plus k square equal to 0. Okay, so m, the two roots will be m equal to plus or minus ik. So hence the solution, general solution of the equation number 3 will be how much? Psi x equal to c e to the power ikx plus d e to the power minus ikx. So from equation number 3 we found the so called auxiliary equation. This is the auxiliary equation. From this auxiliary equation we found the two roots, and hence the general solution will be this much, or it can be written as c into, this will be written as cos kx plus I sin kx, and this can be written as plus d into cos kx minus I sin kx. Okay, so by considering these two terms, this term and this term, it will be c plus d cos kx plus this will be I c minus id, see ic sin kx minus id sin kx. So ic minus id sin kx. Okay, so consider that c plus d is equal to a and I into c minus d is equal to b. So if c plus d will be equal to a and I into c minus d will be equal to b, then this will be written as psi x equal to a cos kx plus b sin kx. Let this is equation number 4, and this is nothing but called as, this is the general solution of this of the equation number 3. Okay, This is the so-called general solution of this equation number 3. Now, so we found that from equation number the general solution of this equation number 3 is equal to this much. Psi x is equal to a cos kx plus b sin kx, equation number 4. Now we have to move for the next page. So in the next page it is written that here a and b are arbitrary constants, and these can be evaluated by applying boundary conditions. Okay, the boundary conditions are what? The boundary conditions are psi x at x is equal to 0. That means wave function, whatever we have been defined here. So here from just previous explanation we found that psi x at x is equal to 0 here, that is psi 1, or the wave function will be equal to 0, psi 1 equal to 0 at x is equal to L and x is equal to x is equal to 0 and x is equal to L. So that is the boundary conditions. So these are the boundary conditions, and these boundary conditions itself can be feasible if we have to analyze this diagram itself. Okay, it could not be penetrated this side, it could not be penetrated this side, means at x is equal to L and x is equal to 0 the wave function could not be exist, and beyond that also not to be existed, and that is the boundary condition. So that boundary condition here we are applying. So psi x will be equal to 0 at x is equal to 0. That implies from equation number that is from equation number 4. From equation number 4 we found that a into cos 0 plus b into sin 0 will be equal to 0. That implies a equal to 0, and the next boundary condition is that psi x at x is equal to L equal to 0. That is from equation number 4. This equation number, this is from equation number 4. This will be 0 at x is equal to L and x is equal to L. So from the first boundary condition we found that a is equal to 0. Okay, so that we have to also consider in the second boundary condition. So a cos kl plus b sin kl equal to 0, and from the first boundary condition we found that a equal to 0. If we have to put a equal to 0, then b sin kl equal to 0. Here b could not be 0, because if b will be 0, then wave function psi x in equation number 4 will be 0. See, in equation number 4 from the first boundary condition we found a equal to 0. So here if we are going to consider b equal to 0, then equation number 4, if we are going to consider a is 0, b 0, then psi x, that means psi x will be equal to 0. So b could not be 0, but sin kx will be 0. Sin kl will be 0. Hence sin kl will be 0. That implies kl equal to sin n pi. We know that sin n pi always be 0. That implies kl equal to n pi, k is equal to n pi by L. Let it is equation number 5. Okay. Now equation number 4 will be how much? Psi x will be equal to equation number 4, that is a cos kx plus b sin kx. So a already is 0, k we found how much? That is n pi by L. So hence psi x will be equal to b sin kx. B sin kx, or it will be b sin, instead of k I can write n pi x by L. So as here n has different values, or for specified value of n, psi x will be exist. Only for that we can write psi n x will be equal to b sin n pi x by L. This is equation number 6. Okay, This is equation number 6. Now we have to consider energy eigenvalue. Now we have to consider, and from this if we are going to consider the normalization, this is the B, here B is nothing but called as the normalization constant, and if we have to consider the normalization condition for this equation, then we can found B, that we are going to discuss in our next class. But up to today class we are going to be discuss energy eigenvalue, and we have to stop over there. So energy eigenvalues, what is energy eigenvalue? Okay, see, from equation number 5 what we found, from equation number 5 we found k is equal to n pi by L. Previously we taken as k square is equal to 2m e by h cross square. Okay, so here I can write k is equal to n pi by L, or k square is equal to n square pi square by L square. K already we have been taken as 2m e by h cross square. K square is nothing but k 2m e by h cross square is equal to n square pi square by L square. Okay, so hence E will be equal to n square pi square h cross square 2m is 2m L square. This E is what? This E is the energy with which the particle is moving in this one dimensional well. That means this is the fully kinetic energy. Okay, there is no force on this, means there is no potential energy, only fully kinetic energy. Okay, so here E is represents the kinetic energy of the particle inside the one dimensional potential box. So here E is came out not a single value, because if E is depends over n, and n will be equal to 1, 2, 3 like this. Here n equal to 1, 2, 3 up to infinite. So for each value of n we can found E have the different value. That means En, so this E is depends over n, so it can be written as En equal to n square pi square h cross square by 2m L square. So okay, so this is equation number, this is equation number 7, and here n equal to 1, 2, 3, 4. Okay, because from equation number it is found that the energy of the particle is quantized in the box. So this equation number 7 represents that energy is quantized. See, here n is equal to 1, then n equal to 2, n value 1.5, n value 2.5, n value 3.5, or n value in between, any value in between 1 to 2 is not acceptable. So here n either it will be 1 or 2 or 3 or 4 like this. So from this equation number 4 it is found that, or it can be concluded that the energy of the particle is quantized in the box. That means only certain values of energy are permitted. Okay, so that here we conclude that energy of the particle inside the box is quantized. Not all the values of n is considered, and the energy is not continuous of a quantum particle which is inside a one-dimensional box. So the minimum energy of the particle inside the box, it is, if it will be represented by E0, then for n equal to n it will be equal to pi square h cross square by 2m L square. Let it is equation number 8. So the energy eigenstates of particle is characterized by the quantum number n is equal to 1, 2, 3. So eigenstates is represented with the help of the quantum number, that is n equal to 1, 2, 3, 4 like this. The various energy values will be how much? Let for n equal to 1, E1 will be nothing but so called minimum energy, that is also represented by E0 will be pi square h cross square by 2m L square, and for n equal to 2, E2 will be equal to 4 into pi square h cross square. This is n square. Okay, n square means n square means 4 pi square s cross square by 2ml square will be equal to 4e0. For n equal to 3 it will be 9e0. For n equal to 4 it will be 16e0. e4 will be 16e0, and like that. If we are going to represent all the energy states, you can see that the E1 is here. For n equal to 1, E1 equal to E0, that is the value of pi square s cross square by 2ml square. Now E2 is equal to 4E0. So what will be the difference between this? What will the difference? Difference is 3, right? Difference is 3. Now what will the difference between this and this? Second and third, difference will be 5. What will the difference between the two energy states, between third and fourth? Third and fourth having the difference of energy will be equal to 7. That means difference between the two energy increases as we have to move towards the higher and higher energy states. So this is our ground state energy, or we can say the minimum state energy. Minimum state energy is E0. Second energy state will be E2 will be equal to 4E0. The gap will be, suppose it is 3, then gap from second to third will be increased, because the gap between second and third, it will be 5. So you have to whatever the space you have to be drawn for the figure from first to second to third, you have to just increase the space. Okay, for third to fourth you have to again increase the space, then 4 to 5 you have to again increase the space. So E2 for n equal to 2, E2 equal to 4E0, E3 equal to 9E0, E4 equal to 16E0, E5 is equal to 25E0. So you can see that in between this the energy difference is 3, in between this energy difference is 5, in between this energy difference is 7, in between this the energy between is 9. So as we are moving higher to higher excited states, or higher to higher energy states of the particle which is inside the one dimensional potential well, then we found that the energy difference between the two consecutive energy states is increases gradually from lower to higher. Okay, but if you can think that here, you can, maybe you are going to think that if we have to move much higher to higher, again much more higher excited state, this gap will be increased. No, actually it is not like that. If we are going to be calculate by taking examples, you can found that this is increases, this is initially it is increases, but higher to higher excited states, this gap again it is comes closer and closer, means the gap is gradually decreases and it will be look like continuous. So from figure 3, this figure 3, it can be found that from figure 3, this is the figure 3. Okay, from figure 3 one can be found that as quantum number n increases, the spacing between adjacent energy levels increases, but at larger n, at enough larger n, at enough at enough larger n, the rate of increase of spacing will be slower. Thus, with larger n, energy levels becomes quasi-continuous. Means it will not exactly continuous, but the gaps will be reduced, and likewise I can show you that initially it will be increased like this. Initially it will be increased, means this like this it will be increased. It will be looks like increases, but whenever we have to move higher to higher excited states, then it will be looks like this. That means I can zoom it for you, you can analyze well. See, it will looks like this. That means the states are discrete, but it is very close with each other. That means it looks like from with a distance of view, from distance view it looks like continuous, but for the closer view it is actually discrete. So only for that it's named as quasi continuous, not exactly continuous, but it is looks to be continuous. Only for that, thus with large n energy levels becomes quasi continuous. Okay, so here we have to stop our discussion today. In our next class or next video, we are going to be discuss about effect of linear dimension of the box. If the box length will be increased, what type of energy spacing is going to be happens. Then eigenfunctions, that suppose this is the general form, and eigenfunctions means here we are going to find out the b value and different states. As we have here, we can see, as we have the stationary states, that these energy states have energy value, this one, that means these energy states have a particular eigenfunction. This particular state also a particular eigenfunction. What are the eigenfunctions and in which way it is going to represent, that we are going to be discuss in our next class. And also next class we are going to discuss about the probability density of the particle in each and every states. So up to here we have to be stop our discussion, and next class we have to start next portions. Okay, so here I can suggest to all of you that you go through this video, pause the video wherever you want, and you have to write down the notes and watch well. If any doubt, you can ask. Okay, we have to discuss. So thank you so much for watching this video. Thank you.